Hello, my name is Ashley Goodnight, and this is my Lab 4 report for Physics 2212. Let's get into our introduction. The purpose of this lab is to predict the behavior of series circuits through observing and examining various simulated circuits. We care about this experiment because it allows us to practice key physics concepts, including the loop rule, charge conservation, and the definition of steady state. In the end, I successfully used the PHYS Circuit Construction Virtual Lab software in order to practice and compare the observed and theoretical values of circuits containing both resistors and capacitors. The first part of this lab took a deep dive into series circuits. We were given the example circuit displayed in the bottom left corner. From this, we observed the various currents and voltages across the circuits. Here were some of the values. In this section, we were asked to make a couple general observations about the findings. I discovered that, number 1, when an ammeter is reversed, the sign of the current is reversed, but the magnitude remains the same. Number 2, voltage in a series current drops across each resistor. The voltage drop across all resistors will add up to the voltage of the power source. The final part of this section asked us to use the voltmeter across all of the components in the circuit. Let's see what I found. I only found voltage drops across the two resistors. Using the values from the simulation above, I plotted these potential drops. Now let's move on to RC circuits. The criteria of this next section of the lab required us to set up a circuit with a 9-volt battery, a 200 millifarad capacitor, and a 30-ohm light bulb. After setting up the circuit in the simulation, I gathered 20 seconds worth of voltage versus time data, shown in the data table. Let's see what its plot looks like. Here's what it looks like when I plot the natural log of delta V divided by delta V0 versus time. We chose these axes in order to make it easier to calculate the RC value. In order to calculate the RC value, I needed to find the line of best fit. Its slope represents -1 divided by the RC value. So my RC value was -33.2166. We were asked whether this computed value agreed with the RC value of the circuit, and for my plot, it doesn't quite. The error is likely due to human error since my reaction time between stopping the simulation and the stopwatch at the same time is way off. Finally, we have two conclusion questions. The first question asks us, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? Well, in the first section, we found that this simulated and quote idealized ammeter had no voltage drop across it. However, in real life, the ammeter would create a minuscule resistance value, causing a slight voltage drop. Let's move on to the second conclusion question, which asks us, what if you were doing this lab in real life and used a battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Let's address the simulation first. Without a resistor, the capacitor charges almost instantaneously, and there's a literal flame over the battery when you try to discharge it. In real life, the capacitor would also charge extremely fast. However, it is important to note that just like the ammeter, the capacitor isn't perfect and also contains a slight resistance. With that, I am concluding my presentation. Thank you for watching.